Is it working? And now we have Niclas Boehmer, who's going to tell us a little bit about elections. So take it away.
Hi everyone, my name is Niclas Boehmer. I'm a PhD student from TU Berlin in Germany, and this is joint work together with Bredereck, Piotr, Faliszewski, and Rolf Niedermeier, and it's about the robustness of real-world election winners. So let me start by introducing what an election is. I mean, it's a colloquial used term, but for us it's a kind of a very specific mathematical object. In particular, an election for us is defined by a set of candidates. So for example, a tent, a cap, and a ball, and a set of voters. For example, here, a blue voter, a black voter, and a red voter. And each voter gives us some strict preferences over these alternatives. For example, so here the blue guy prefers to the tent, to the cap, to the ball. These voters can be, for example, humans in a political context, but can also be some agents or some other entities. We will later see some examples of that. And then the task that we typically face here is that we want to determine a winner of this election. So in most of these contexts, we have a single winner election. So we just want to say, okay, this candidate is the winner of the election. You are now, you can be happy, you can do some task. I don't know, it depends on the application. And one very popular method, or one kind of class of methods to determine such single winners, are so-called scoring-based methods, which take as input an election and a vector, which is just kind of, contains some numbers. And then we do the following. Each voter awards SI many points to the candidate it ranks in ith place, and the candidate that in the end got the highest number of some points wins the election. So for example, one very popular rule that is also used in most political contexts is the plurality voting rule, which corresponds to the scoring vector starting with a 1 and then all zeros, which basically just means everyone gives 1 point to its top choice, and then the one that receives the most top choice votes basically wins. So in this context, this would be the tent, because the tent has 2 points, the ball has 1 point, and the cap has 0 points. And now we are interested in one specific feature of these single winner elections, and this is how robust or how close they are. I think this is also a matter that is sometimes discussed in public after elections. I mean, just kind of how, oh, this election was really close, this election was not so close. I mean, especially also in some presidential elections, it's very actively discussed afterwards. And we are now doing, or we are kind of try to quantify a very specific interpretation of what it means to be close. And particularly, we are interested in the robustness of election winners with respect to random equiprobable noise. And what we mean by noise is basically just we select some voter, we select some candidate in its vote, and then we swap this candidate with some of the adjacent candidates. So we basically swap adjacent candidates in some votes uniformly at random. And this is kind of how we model noise. And the reason why we believe this to be interesting is kind of twofold. The first interpretation is, okay, I mean, voters' preferences depends a bit on the implication, but for example, change over time. I mean, they could get some new information at some point, so they might change their preferences. And kind of, I think this view implies that the robustness or closeness of an election also influences the legitimacy or credibility of the election winner. Because I mean, if you won the election by a lot, then I think you have a pretty strong, for example, political mandate. Whereas if it was really, really close, then people might say, oh, you probably shouldn't be allowed to implement huge changes, because if we would have voted 1 week later, it's unclear who would have won in this case. A second, even more drastical interpretation is basically assuming that casted votes only capture reality approximately, because, I don't know, some people weren't able to vote, some votes were not correctly casted, or some people made up their minds spontaneously. In this case, I think one could even go one step further and say, okay, if we detect an election to be close, then this even requires active countermeasures like re-election or recount of the ballots, or stuff like this. And overall, we hope that we increase the transparency and fairness of elections by kind of better understanding how robust winners are and how close these elections are. There are also already some measures introduced in the literature where people have looked at different things, how to measure the closeness. And I think the most popular one, especially in the context of these scoring-based protocols, is just to consider the score difference. So we just kind of subtract we look at the score of the winner, look at the score of the candidate finishing in second place, we calculate the difference, and then we say, okay, if it's like 3, it was close. If it's like 20, then it's not so close. But it's kind of a bit of an intuitive way how to do it. A slightly more complicated view or a slightly more complicated measure is known as destructive swap bribery. That's a bit more technically involved. Here we basically ask for, you are given the election, how many changes do you need to make in this election? So how many swaps of adjacent candidates do you need to make for the winner to change? So you are given full control over the input. How much change do you need to make such that the winner changes? And in previous work, we have found that these two approaches are basically in practice very closely correlated. So they basically boil down to the same thing. And both of them are kind of worst case focused, because, I mean, you're given full control. I mean, this destructive swap bribery problem, for example, you're given full control over the input and you could do everything that you want, and you are kind of asking for, yeah, this worst case view. Whereas we now propose to use this average case view. I mean, this random equiprobable noise, which I believe to be more the things that are really happening in practice, because usually you don't pay people to, adversarial change their preferences. So to get into a bit more of details, we looked at elections from different sources and analyzed for each of them the robustness as follows. We consider different perturbation levels. Each perturbation level basically corresponds to a certain degree of noise that's introduced. I won't go into detail here because it's a bit technical. If you're interested, I'm happy to talk about it afterwards. So we took a perturbation level, and for each of these perturbation levels, basically we generated multiple elections where we made these random changes, and then we recorded the average winning probabilities of the candidates in these different levels, and then we get graphs like this. Here we have kind of on the x-axis we have the level of perturbation, and on the y-axis we have the winning probabilities of the candidates, and each of these lines corresponds to one candidate. So for example, I mean, the red guy is, and this will always be the case, the red candidate is always the winner of the initial election. I mean, initially, when we do no perturbation, we have only the initial election. The red candidate wins this election, so its winning probability is 100% here. And now if we move kind of from 0 to 1, we make more and more random changes in the election, and then we can see how the winning probabilities of the candidate changes if we do this. And we believe that this kind of slope gives us some insights into how robust the win of the candidate is. So for example, here it goes down rather slowly. So we will later see also examples where it changes much, much more quickly. But sometimes we also just want a number to put at an election to quantify. I mean, these graphs are nice to look at, but sometimes we just want a number that quantifies, okay, how robust is this election? And for this, we propose to use the so-called 50% winner threshold, which is the lowest perturbation level such that the winner's winning probably drops below 50%. In this case, it would be, for example, 0.8. I mean, here, the red guy doesn't win anymore more than half of all cases. And in our work, among others, we looked at two different types of elections. The first one are so-called Formula One elections, which originate from Formula One championships. So we looked at 38 editions of the Formula One championships. And each of these editions is basically structured as follows. We have some drivers, and they compete in different races. And now we basically view the races as the votes and the drivers as the candidate. So basically a vote corresponding to a race ranks the driver finishing first as the first candidate, driver finishing second as second candidate, and so on. And that's actually what they also do in practice. And they use some nice scoring-based voting rule then to decide who's the overall winner of the competition, so who's the Formula One world champion. Which is also kind of why we selected this data, because we could really use the actual rule that they also used in practice. So for example, between 2010 and 2018, it's always like, okay, if you win a race, you get 25 points. If you finish second, you get 18 points, and so on. And then we took these 38 elections and basically looked at them from our robustness perspective, and we were quite surprised to find that they overall have a very low general robustness. I mean, these numbers probably don't mean to you a lot, but I will later show you some examples that make this a bit clearer. But we were surprised that they have a low robustness, and in particular, we find numerous very, very fragile election winners. And this is also now what I want to expand on this slide, basically showing you different types of very, very close election winners. So here, each of these plots corresponds to 1 year, and here we always have the legend, we have the scores, so the number of points that they got overall. And all of them, so I will now show you 6 elections, and in all 6, it will be always the case that already just very, very few random swaps change the winning probability substantially. But the change that will happen is of different type. And here, these are probably the most extreme elections, because here you can basically see, okay, we just make few changes, and the initial winner stops to be the most probable winner. Someone else actually will become the more probable winner if we just make few random changes. And I think in these cases, one could even say that the original election winner was winning the election more by luck or by accident than by true merit. And the interpretation that you kind of need for this is, okay, you can picture the election that we actually observed at some point, and then you can look at the close surrounding. That's basically what we are doing by sampling and perturbing it a bit. So we have kind of this point, we have the close surrounding, and actually a majority of the points in the close surrounding are won by someone else. And then coming from the perspective that our elections, our votes only always capture reality approximately, this basically motivates to say, okay, in these elections, maybe the blue candidate was actually the stronger one and should have been declared the winner. To make it a bit more concrete, in this election, for example, making around 5 random swaps changes the winner with 22% probability, which we were quite surprised about, because, I mean, again, this is not a super small election. We have like 22 or like 20 votes, 20 candidates. And we make these 5 swaps at random. So this means in particular that a lot of these swaps won't even involve the red guy or the blue guy. So we previously observed that for this worst case focus view, there are 5 swaps. I mean, doing artificial swaps is usually quite powerful. But we were also quite surprised to find this from this random and more average focus perspective. Then we also have a different type of closed election, which we call implicitly tied elections. So here we basically have that the winning probabilities of the 2 top guys become very quickly very, very similar. So I think one could say in this case that we have fragile winners, where in fact the top 2 guys are actually of equal quality. Here giving you another example, in this 2007 election, just making one single swap changes the winner with 5.6% probability. Again, a lot of these one swaps that we make won't even affect one of the strong candidates and will therefore always contribute to the status quo. And lastly, we also find elections where we have some fragility. So also here we have quick changes even after just making some random swaps, but nevertheless, the original winner is still the one with the considerable higher winning probability. So one can say, okay, the winner was a bit fragile, but his win is still grounded in solid support because he's still a lot stronger than all the other guys. Okay, and then in the second analysis, we also looked at some political elections. Unfortunately, we cannot really look at real political elections because, I mean, probability is used and people only cast their top choices, so we don't know their full preferences. So for our kind of analysis, we would need to know, but yeah, we don't. Which is why we basically use some, I mean, it's some meta elections, and they work as follows. We look at Polish city council elections, and they are district-based, so each city is partitioned into different districts, and each district elects its own representative. And each representative here can be clearly mapped to a party. And now we basically obtain one election per city, where we have a voter for each district, and the voter for district ranks the parties according to how the candidates of the parties finished in this district. So for example, if we have a district and the candidate from party A won, this is the candidate who the district ranks in first place. Then if candidate from party B came in second, then they rank party B in second place. And now if we apply the probability voting rule to this, then basically the score of a party corresponds to the number of seats that the party gets in the parliament. And this implicitly also says the election winner is now the strongest party. So the party with the highest number of seats, which has some particular importance in this context because it's the party who is usually trusted to form the government and stuff like this. Now here, in this model, our random changes that we do, so these swaps of adjacent candidate basically means that in a district, 2 candidates now finish in different order from each other. And again, yeah, we analyze the robustness, and here we find that these elections, for example, in contrast to these sports elections, to the Formula 1 elections, are actually of quite high general robustness. So you remember this 50% winners threshold? It was before for the Formula 1, it was 0.18. So here it's much higher. We only have very few fragile winners, but nevertheless, it's maybe still worthwhile investigating because there are still some interesting patterns you can observe. So for example, here we have 2 elections which are still close-ish. I mean, not as drastic as what we have seen with Formula 1, but nevertheless here, I mean, especially this region is interesting where you just make few swaps, and also here we have at least some change. So it could have been with some random changes, there is a certain probability. For example, here again, to be a bit more concrete, making one swap uniformly at random changes the winner with 4.6 probability, which again implies some non-robustness. Some other takeaways, just being a bit brief here, that we have is that the score difference is basically not really able to identify these different patterns. So for example, here we have an election with a score difference of 3. I mean, it's close-ish. Here we have an election with the score difference of 1, but nevertheless, the initial winner is much stronger than the other guy. So this, our average case view really offers a new perspective on this whole question of the robustness, which is different from the established scoring-based scoring difference measures. And lastly, we also found that a lot of these Polish city council elections are tight. So actually 124 of these elections are tight. And also here, our view has something interesting to tell, because sometimes the original winners, their winning probabilities behave very similar. So they are of similar strength. If we start to make some swaps, they behave similarly strong. Whereas in other cases, there's this clear difference between their behavior. So here, for example, I mean, the red guy is substantially stronger than the blue guy. So one could say, I mean, if a tie-breaking needs to be chosen, then maybe, for example, in this election, choosing the red one to be the single winner would be a bit more justified, because actually, yeah, if some changes would have happened, then his winning probability would have been higher. Okay, so to sum up, what have we done? We have analyzed the robustness of real-world election winners. We found numerous fragile real-world election winners, and we're even able to group them into different categories. In the paper, we have also done a bunch of other things. For example, we have analyzed the robustness of different voting rules, but yeah, I haven't shown you that. And for future work, it would be interesting to further explore the capabilities of our view as a tie-breaking mechanism. I mean, basically building up on the two last plots that I showed you. Also looking at the weighted model would be pretty cool because, I mean, maybe not all swaps happen with the same probability. And lastly, yeah, it would also be great to look at political elections with using full preferences of voters. I think here some polling data might be the most promising source. Yeah, if any of you have some data available, I would be very happy to know. And yeah, with this, I want to thank you for your attention, and I'm happy to take questions.
Hi, very interesting talk. How do you think about the sort of, I guess, the robustness of the results to like the noise model you choose, or like how you do the swaps and so on?
So yeah, I think I have to speak of some technicalities to answer this question. So we are using actually the Mallows noise model. I don't know whether you've heard of it. It's kind of the standard for using for modeling random equiprobable noise. We have in a previous work also looked at a model where we really do a specific number of random changes, but this turned out to be computationally quite expensive. That's why we use this Mallows approach. And those two approaches perform very, very similar. So yeah, and we actually did some kind of verification. Also, for example, saying, okay, we just do one random change per voter. So basically not allowing a different distribution. Also, this produces very similar results. So it's kind of robust to the noise model that you have. But we always assume some kind of uniform assumption. So for example, we haven't looked at what happens if we give more probability of switching the bottom ones, which we probably should do at some point to see what comes out there.
Hi, thanks for the talk, very interesting. Which tools are you using to solve these kind of problems, to do the swaps? Which models, like, you know?
So we are what we are using here is the so-called Mallows model.
Yeah.
So the Mallows model is a model to sample votes, where you basically have a central vote, and sampling a vote is the probability of sampling a vote is then proportional to its distance to the central vote. Where distance means the swap distance, so the number of swaps of adjacent candidates that you need to make to transform this one vote into the central vote. And what we are basically doing here is we're taking each vote, pushing it through this Mallows model, so basically sampling one vote from the Mallows model with this vote as a central candidate, as a central vote, and then we're basically replacing this vote by the sampled vote. Yeah, I'm happy also to discuss it in more detail afterwards, but it's kind of not super straightforward, maybe.
Thanks.
And do we have the next speaker? Just we can keep going with questions. But the
Hi,
next speaker.
Nico. Very interesting work. First question is, I'm interested in what's the relationship of your robustness and stability of the Boolean function when you only have two candidates.
What do you mean by stability?
So I think in Boolean function analysis, you can also perturb each Boolean input randomly with certain probability, and you want to ask when will the outcome of this Boolean function swapped. And a very well-known result shows that the majority function is the most stable one when you flip those bits independently.
We haven't looked into this. So
okay,
I cannot really give you a justified answer. Intuitively, I would expect that they are kind of correlated.
Okay.
But I'm very happy to discuss this in more detail offline and hear your thoughts.
And the second question would be, what is the most stable one? Can you give me some hint
Border.
about
I mean, so very briefly, I've kind of summarizing this different voting rule kind of thingy. The more information you take into account from the votes, the more robust is your voting rule. So plurality is, for example, very non-robust. And kind of the more a single swap can matter, also the less robust is your voting rule. So if you have large gaps in your scoring vector, then this will lead to non-robust results. Actually, we also found, we also analyzed this Formula 1 elections a bit more detail because they also use different scoring vectors, and this was kind of interesting to observe also similar phenomena there.
Yeah, thank you very much.